and thank you for the dry run. I appreciate it. Um, I did kind of tone this down, of course. I do know this is an undergraduate crowd, but I hope that there is enough complexity for some of us that it will be pretty enriching. So I'll be talking to you today about the work I've been doing, mostly with the European Spallation Source in Lund, Sweden, but also Oak Ridge National Laboratory here just outside of Knoxville in Oak Ridge, Tennessee, pertaining to free neutron searches for beyond standard model physics. So with that in mind, if I can advance here, great. I'm going to give you some background on a particular process that we're looking for in both of these places that can have very rich implications for us in our understanding of fundamental physics. So we understand, of course, that the matter-antimatter asymmetry of the universe is a big problem. Basically, the most interesting kind of fundamental fact about the universe that we see today is that it exists at all. If we go from a kind of naturalistic perspective, this is quite a surprising statement, and there's key ramifications for the fundamental interactions that we want to measure in nature because of it. We know today that the universe is basically flat, as in has effectively zero net energy density. We know it's expanding, and we know it's principally made of matter, but also dominated by dark matter and dark energy, both of which we have very little understanding of, but I'll be coming back to dark matter. And the problem with this is that we don't understand this context when we think of kind of getting a universe together at all. We don't understand how the Big Bang actually occurred, and we have trouble understanding, especially the matter-antimatter asymmetry, because if we assume that we started from some kind of a charge symmetric state where we would have all masses and number densities of particles were balanced, we had equal decay widths of particles and antiparticles, and equal and opposite electric charges of the particle-antiparticle pairs, then this would seem to imply that we would have effectively everything annihilate away at some point. So how do we take this symmetric state and create something that is asymmetric out of it? This is kind of the key problem, and leads to a good proposal of potential new phenomena that we can search for in a beyond standard model context. So the question that we're asking is, what things can we learn from this predominantly matter-dominated universe? And so we call this problem the baryon asymmetry, or the baryon abundance problem. It's been confirmed in a multitude of experiments, but primarily from the cosmic microwave background, as well as cosmic ray observations of protons dominating antiprotons at about a 10 to the 4 ratio. But the big thing comes from the cosmic microwave background not simulation, but measurement of the Planck experiment, I should say, where they measure a quantity called beta. And beta is basically the ratio of the difference between baryons and antibaryons to cosmic microwave background photons. And we find that this number is of the order of 10 to the negative 10, where we effectively assume that we have no antibaryons from our local group, and also just from the fact that we don't see high energy gamma rays that would come from any kind of annihilation signature of matter and antimatter meeting in outer space somewhere. And this is kind of very problematic as a number, because if we do the calculations ourselves from what we understand about standard model physics, the thing that we would think would happen is that you would have mutual annihilation after the Big Bang of all of the matter and antimatter down to what we would call a freeze out temperature of about a mass of a nucleon. So that would be something like a neutron or a proton, where we could start making stable matter and nuclei, et cetera. And if you do the calculation, you can find that you would expect that the number of baryons would equal, of course, the number of antibaryons. And you would expect that that number be roughly not 10 to the negative 10, but 10 to the negative 19. And just as a kind of comparison of those numbers, the way I like to explain that to students is that this is basically like Bill Gates's lunch. It doesn't really matter all that much, but that's how much smaller these numbers are. And so we have to explain effectively, not a factor of 10 to the negative 9, but a factor of 10 to the 9 difference. We have this much more matter than we expect throughout the universe. And so this leads us to a thought that we have to come up with some new phenomena to look for to explain this. So this leads us to what we call the Sakharov conditions, which basically were put forward in 1967 that would encapsulate all of the principles that underlie the existence of a universe like ours. This is Andrei Sakharov. He worked on the hydrogen bomb in Russia, later became an anti-nuclear activist, and was quite a raconteur. This is him speaking at the United Nations. Basically, he said that in this wonderful paper in 1967, which is only about 3 pages, and I think has over 3,000 citations at this point, that you have to have a few key ingredients to create a universe like ours. You have to have something called CP violation or CP non-conservation, where basically that means that you have different kinds of interactions for particles and their antiparticles. They don't behave exactly the same way. And this has been basically demonstrated in something called kaon oscillations. I have a nice overview here for students if you're interested from Fermilab. And these are very rich experiments, very difficult to do. There's also departure from thermal equilibrium that we need to have in our decays of our particles in the early universe. And this is usually thought of as being provided by the expansion of the universe. Basically, as you increase the volume of the universe, this becomes easier. And this is basically demonstrated by things like the cosmocroid background. The problem is, of course, that then the third ingredient that we need is something called baryon number violation. We have to come up with a way of having an excess of baryons, matter, over antibaryons, antimatter. And this means that we have to violate this number, which is generally conserved within the standard model, but it's still never been seen experimentally. And this, of course, leads to kind of a sort of holy grail for beyond standard model physics that we want to search for. And I think this would be kind of the key focus for Sakharov, if you ask me. All right, so the interesting thing, though, about the standard model, I kind of lied to you, is that the baryon and lepton number, so baryons are like neutrons and protons, leptons are electrons, muons, neutrinos, etc. They each have an associated charge called a number, a baryon number or a lepton number that's generally conserved within the standard model, but you can violate it infinitesimally, very, very small amounts of violation in something called anomalies within the electroweak sector. I won't go into that technically, but I'll show just a little bit of a sketch of the idea here. So this was brought up by Tufte in 1976. And basically what he said was that when you got to very high energy scales, non-perturbative energy scales, temperatures, you can, instead of conserving baryon and lepton numbers separately, where you would not be able to convert a neutron into something weird or a proton into something weird, you wouldn't be able to make it disappear, basically. Instead, what he said was that you conserve a new quantum number called B minus L, baryon number minus lepton number. And that means that any process is going to be governed at non-perturbative scales by a change in baryon number accompanied simultaneously by a change in lepton number. And that means that you can kind of have a little bit of baryon number violation. And people got very excited by this because they thought these were the ingredients necessary that would confirm Sakharov's conditions and be able to explain the universe that we see today. It turns out that that is very difficult within the standard model context, usually within something called electroweak baryogenesis, to do fully consistently. But people have tried and people continue to try, but usually they do go beyond the standard model. The reason that it's difficult to do this, to remedy this problem within the standard model, is a little bit complicated, but it has to do with the Higgs field. And the Higgs field has a particle associated with it, of course, the Higgs boson. And the mass of that particle tells us a little bit about how the Higgs potential evolved during the early universe's development. And basically what you can think of as the Higgs potential as some kind of barrier in quantum mechanics, some kind of periodic barrier, though it would be actually changing in time and temperature. But if you were to create a universe in what is called a topological vacuum state that's associated with a single baryon number, what Tufte saw was that you could actually have an amount that would be different if you were birthed in a different topological state. And that means that you can quantum mechanically tunnel through the barrier. It's actually just it's a first semester quantum problem in some respect. And what you find is that in order to tunnel through, to start from one baryon number to go to another, it becomes infinitesimally small. The rate of that tunneling is about 10 to the negative 170. So the problem is that this new technique of creating baryon number violation was basically inadequate to see the kinds of changes in baryon to antibaryon ratios that we see today. There is another thing that one can do, and that is classical motion over the barrier, like in just a normal kind of physics problem with a rolling marble. And the problem with this process known as the sphaleron is that it happens at relatively high temperatures, and there has been lots of work that shows that this asymmetry that would eventually develop from this process actually gets washed out eventually and kind of goes to zero, which is a problem. So both of these methods are inadequate, which means that we truly have to go beyond the standard model and actually ask a new question, which is, if we proceed by contradiction, whether or not we should not just violate B, baryon number, but actually violate this new conserved quantity that Tufte came up with, like B minus L. And more generally, we can go about looking for delta B not equal to zero processes, but in general, we want to think of B minus L violation as well. So going beyond the standard model, there's a lot that we can add. Proton decay has been very historically popular. This is one of those diagrams where you take 3 quarks, you have a spectator quark, which later goes into a meson, and then you emit a lepton, an anti-lepton, I should say. This has a lot of rich history, primarily in grand unified theories, SUSY as well. And the LHC has been looking for any kinds of signals that would be related to SUSY, supersymmetry, I should say. But there's no evidence of these kinds of particles, and also very large volume detectors have not been able to observe this rare process. There are other kinds of baryon number and lepton number violation searches, of course. The one I'll be talking to you about today is what's called delta B equal to 2, or baryon number violation by 2 units. And one of those examples is what I'll talk to you today about, which is things like neutron anti-neutron oscillation, which is where you take a neutron of 3 quarks and you convert them into 3 anti-quarks, like an anti-neutron, for instance. This would not be possible with a proton going into an antiproton because of charge violation, but it could be done with neutral particles. There's also other prospects within delta L equal to 2 physics, which is very much related. And this, rather than dealing with theories of baryogenesis, actually deals with theories of leptogenesis. But this is itself a whole other talk that's of quite large interest. But here you have quarks that are actually basically converted into just electrons and other quarks, where no neutrinos are emitted through this beyond standard model mechanism of neutrinoless double beta decay. All of these, though, ask the question of how we prioritize them. Historically, there have been tens of proton decay experiments, tens of delta L equal to 2 neutrinoless double beta decay experiments, but why not other kinds of baryon number violation? And especially if they can directly, theoretically, remedy the baryon asymmetry of the universe, the baryon abundance, and potentially be observable at very low energy scales that we can actually test in the laboratory. And so one of those processes that matches all of those conditions at low scale and can be used for prodigious amounts of experiments with prodigious amounts of free neutrons, for instance, is neutron anti-neutron transformation or oscillation. And the prime idea here is that the neutron itself actually has a small admixture of what we call a Majorana component. In other words, it's slightly a little bit an antiparticle itself. And it evolves according to kind of an effective Hamiltonian that I've written down here, which depends on a few things like the mass of the neutron, the magnetic moment of the neutron and its decay width, as well as this delta M, which is a admixture term. If you do the probability calculation of this, it's approximately t over tau squared, where t is any observation time, how long I'm looking at this neutron, versus the oscillation period that we expect for this process of n oscillating into n bar. Now, from a quantum field theory perspective, other mechanisms exist, of course. One of the key mechanisms, the popular ones today, is what's called post-sphaleron baryogenesis. I briefly mentioned the sphaleron as being something that washed out baryon asymmetry in the early universe. So if this process happened at a low enough energy scale, post-sphaleron, after any of those processes went out of thermal equilibrium, then you can actually come up with interesting ideas in the early universe where you can have decays of heavy scalar particles where you actually produce matter out of this scalar portal, and you can create neutrons or antineutrons this way. And if you include CP violation, for instance, and at these low energy scales, then these interference terms can lead to the proper baryon abundance that we know and love. So under proper laboratory conditions, the idea is that if we were to mitigate any of the kind of excessive environmental fields that existed, like magnetic fields, for instance, from the Earth, if we were to suppress those under proper conditions, then basically you're just dealing with a matrix here that has effectively nothing that would split the states between two different energies. In other words, if you had a neutron and an upper level energy and an antineutron at a lower level energy, you would be able to actually make these energies the same and induce the oscillation just as you would in a normal kind of quantum mechanics problem. So this is fascinating, but it's difficult to achieve, of course, getting magnetic fields like this very close to zero. Especially if you want to maximize the time that you observe the neutron in a beam, because it's going to be traveling downrange at a few thousand meters per second, and you have to, over this very long range, have very, very low magnetic fields and very high uniformity, which is difficult to achieve experimentally. I will also just mention that you can do this within nuclei, but it is difficult, and people are still working on it, as well as myself, by the way. But another kind of interesting point here is that you can look through the literature on post-sphaleron baryogenesis. And the interesting thing about the theory is that if you look at the probability of a particular oscillation time occurring, you have both a lower limit and an upper limit to this theory. And this is an overly constrained theory in some respect because of contributions to other standard model mechanisms that would be expected, such as meson oscillations that can be measured at experiments like the LHC. And what that means, though, is that we have a finite range between where we are and where we can go for possibly eliminating the theory and moving on to trying to investigate more exotic mechanisms that could remedy the baryon asymmetry. Just to briefly go through here, there is a way to relate the free transformation time, tau n and bar, to the intranuclear, kind of inside nuclei oscillation period through something called a suppression factor, R. I won't go into this, but the idea is that we can do different kinds of experiments in large detectors and in free neutron beams that allow us to observe the same physics. So if you look at Super Kamiakonde's data, back in 2015, they published a limit that is way, way low. It doesn't even come on to this particular parameter space. If you look at the capacity of experiments like DUNE, which we hope to be coming online in the next 5 to 7 years using liquid argon for intranuclear targets, if we have similar background levels to Super K, we would expect this. A new recent study from DUNE came here, and then another came here, and I will be publishing something soon about trying to better understand this wide range, but that's coming up in the next couple of months. As far as where we could go with DUNE, though, the upper limit from what we think DUNE could do would be somewhere here. So we start to probe this first kind of probability maximum where we expect that the oscillation could be in this particular range. If we look at free neutron experiments like at the European Spallation Source, if we were to run for 3 years, with just the normal baseline that we currently have planned, which I'll briefly show you in a little bit, we can get here. And if we improve with something called an anti-neutron reflector, which is under development right now, theoretically, we could actually go through the full first maximum, which is very encouraging. And actually, with a few more years, we would be able to get actually to the full part of this parameter space, which is very encouraging. So just as a summary here, basically we start from one theoretical start point of looking at the baryon asymmetry and understanding that the baryon number violation process that we're interested in could involve neutral particles like neutrons. And that could provide us a good understanding of the existence of our universe to begin with. There are different experiments such as Dune, for instance, but also free experiments like Inanbar at the European Spallation Source, which can promise greater reach in these things. And I'll go through these in a little bit. I want to do one more process with you. There is interesting kind of beyond standard model interactions that new models propose, and neutrons are really good tools to test these. When we map different kinds of beyond standard model quantum field theories onto low energy phenomena with the neutron in mind, we can think of different kinds of behavior, like oscillatory behavior, that can test very important things like fundamental symmetries, but also other portals to dark matter, for instance, which I'll talk about. And so we just recently went through how we could have a small admixture of an anti-neutron component, a Majorana component, inside of the neutron wave function. We can also think of other kinds of admixtures that can be proposed here that are today quite popular. You can think of neutron disappearance, for instance, or neutron conversion into dark matter, where you would have basically a neutron disappear into a dark or parallel sterile sector. And this could have key implications, not just to dark matter existence, but also the particle nature of dark matter, I should say, but also something called the neutron lifetime puzzle, which I'll briefly review. Then we can also even think of even larger systems. We can think of admixtures of all of these. And this kind of gets to another heart of a problem that we have in particle physics, which is if we are only thinking about the standard model and only our ordinary matter sector, it's very difficult to actually come up with any kind of grand unified theory that encapsulates just ourselves, because dark matter is such an important component of our energy density that we see. And to ignore it as far as the evolution of our universe is probably very naive. And so there are wonderful prospects to test all of these ideas at Oak Ridge, at the high flux isotope reactor and Spallation neutron source, as well as ESS with what we call the high beam beamline. So there's strong evidence for dark matter. We all know this probably. Primarily, the thing that most people know is that we have this excessive amount of rotational velocity that we see as we go farther out in distance from a galaxy. I have a little illustration of that, or an animation of that, where we can see basically the difference between these two is that we have a large amount of dark matter here. That's the purple, pink kind of colored, that density. But if with a low amount or kind of zero, you don't get the same kind of curve. You don't have this greater acceleration that you see. So is the other kind of issues, of course, with dark matter is gravitational lensing. We don't see luminous matter where we should at large distance scales. There's things like the bullet cluster that give us hints. There's also a need for the cosmic web, as far as if any of you know what the Millennium Simulation is, I believe it's called. Basically, you don't get these very kind of fine tendrils that we see at the large kind of cosmic scales without adequate dark matter. Also, it's a key component, a key ingredient for our cosmic microwave background. We wouldn't be able to predict what we predict and also match what we think from the data without a dark matter component. And from all of these things, we surmise that dark matter makes up about 25% of the energy density, while our own ordinary matter makes up only about 5% of that. And this is, of course, a gigantic quandary that we have to be able to explain, let alone even try to understand dark energy. There's also a problem within the community searching for the particle nature of dark matter to confirm the particle nature of dark matter, which we expect from quantum mechanics. Uh, Basically, there's only a few, what I would say, controversial positive results. The chief one among them, or the one that's most well known, is the Dama result, which I believe is up to a 12 sigma observation now. And basically, but they're the odd man out. Everybody else disagrees. They don't think that they're observing anything. And as you can see in this plot of cross section, which you can think of as kind of the interaction rate that you expect for the particles impacting on nuclei, the dark matter particles, versus those dark matter particle masses, then what you see is that we are encroaching on something called the neutrino floor, the neutrino background. And this is very difficult, we think, to go beyond, though there may be techniques to do so in the future. Basically, we are having this crop up here of relatively low masses and very low cross sections. And this means that we're having to go to lighter and lighter masses, and we want to potentially have something maybe of the same order as the mass of a nucleon, for instance, that would be of interest to us. Now, so we need more light, kind of non-weakly interacting massive particle dark matter searches. And so we could think of different kinds of things that are of that similar mass, but everything here we have to understand is highly, highly model dependent. The other problem here that ties into this is something called the neutron lifetime puzzle, or the neutron lifetime anomaly. And basically, there is now approaching a 5 sigma, I think it's close to 4.8 sigma now, disparity between beam neutron and bottle neutron lifetime measurements. So the way that we would do this basically is that we have a beam of neutrons, we have a known length, and they fly through, and we count how many fly through. We count them at the beginning, we count them at the end. And if there's a disparity, then we know that some of them have decayed to a proton, electron, and electron neutrino in the normal neutron decay mode. And so that difference, that disparity, tells us over that length basically how often they're decaying, their half-life, if you will. The other way of doing this in a bottle is that you basically pour in very, very cold, very slowly moving neutrons into a bowl, into a bottle, and you know how many came in, and then you count and you hold them for a period of time, and then you count how many are left at the end. And then that disparity again tells you the difference between the two measurements. So here in blue, we see the lifetime measurements from the neutron beams, primarily done at the NIST facility. And then we see in this gray here, we have the bottle measurements. And as you can see, it's quite large. And if you take the averages of these, you find that there's a 4 sigma disparity here. This is another way of visualizing the same thing. There's something called VUD, which is the CKM matrix element of the up quark changing into the down quark, which is a key, which basically is what happens when a neutron turns into a proton. And then this is versus the GA, basically the axial coupling constant. And as you can see, these two lines here between the ultra-cold neutron bottle measurements and the beam measurements are quite different, and they actually have relative consistency at different times with different measurements of each of these parameters, which is quite problematic, of course, but makes it for very interesting, rich physics searches. And the question, of course, is which one do we want? Do we want to move to this particular place where these show consistency, or is it that we are actually closer to here? This is the question. So understanding the potential beyond standard model sources of these tensions is really great to create high impact science and really enriches the beyond standard model physics searches within the community. I'll also just mention something really quickly. It appears that you can separate them even further. There's actually differences in not just the beam measurements, but the different types of bottle measurements. And this, again, seems to hint at something new is going on. And of course, the perfect thing to search for here is a potential dark matter connection. There's a theory of nature known as the mirror matter hypothesis, which is a dark matter theory, where you hypothesize that the ordinary sector of our normal standard model is mirrored by our dark sector, the one that is parallel to our own that we know makes up about 25% of the energy density of our universe. And we suppose that there's some kind of symmetry between the two where we have all of the same particles, similar parameters, similar couplings, et cetera. And basically that they evolve according to the same, what we would call Lagrangian, if any of you have had mechanics yet. But basically we would have our normal standard model Lagrangian, which governs our normal particles of the standard model. Then you would have some new primed mirrored dark sector here, and then a particular admixture that would accompany these two sectors together that could weakly interact the two of them. And basically the idea here is that if this mixture is very weak, then the mirror sector is dark, it's sterile to our own, from our own perspective, and gravity would be the only thing that would communicate between the two. There's other interesting facts that you can create different kinds of galaxy halos this way that seem to match with what we understand for dark matter, et cetera. And it's also a natural conclusion within string theory where you can have a bulk that allows for parallel branes to actually have interesting kind of connections to other branes. And all of this is through what we call a Z2 global parity symmetry. Another interesting thing is that if we have one or more inflatons that basically create the two parallel sectors here in the early universe during the Big Bang, and the dark sector is slightly colder, the temperature is lower, then that basically means that it looks as though it's older, which not only helps us understand the potentiality of having a kind of a different galaxy halo than we would expect, but it also means that we would have an abundance of things like hydrogen and particularly helium over our own in this different sector that could be at that low mass scale that we would want to be able to search for in our dark matter experiments. The other thing that we can have within any kind of mixture Lagrangian is what we call neutral particle oscillations. So we can actually have something similar to neutron anti-neutron transformation or oscillation, and we can have basically a neutron disappear into the dark sector through this oscillation phenomena. Very similar principles here, where we have, again, some kind of splitting between the two states in energy related to their magnetic moment, any kind of magnetic fields, etc. And then we have an admixture term here on the off diagonal epsilon. And in quantum field theory, you can represent this through the insertion of scalars and also right-handed neutrinos for the experts in the room, but you can come up with theories that allow this kind of transit, disappearance, decay into a dark sector. Now, the magnetic field thing here is interesting because we have, of course, an Earth magnetic field, and there could also be magnetic fields in the parallel sector that we have, the dark sector. So this B prime is in principle non-zero. So what that means is that if we want to do the experiment properly and we want to be able to bring these states into coherence where we have the same energy level and allow the oscillations to occur, that means that we not only have to we can't eliminate the magnetic field in the dark sector. Then instead what we have to do is we have to bring the magnetic fields together in a very, very coherent way where we actually want them to align in some way. So we'd have to scan over the magnetic field directions and strengths, et cetera, in order to induce what's called a resonance condition, which is encapsulated in this particular probability function here, where if you recognize these are basically sinc functions. And sinc functions, SINC, have nice resonance profiles that we would be able to probe at different values of magnetic field and at different angles, which allows this to be a very phenomenologically rich experiment. So basically, there's a lot of work that has gone into all of this. There's tons of relationships between these kinds of experiments, in particular things like axions and supersymmetry. There's other hidden sectors, mirror sectors, dark sectors that also can allow, for instance, for co-baryogenesis between the ordinary matter and the dark matter sectors. And again, this is kind of hinting at the larger problem, right? It's like, how do we understand dark matter? Is it a particle? But also, how do we get the universe that we see today and the abundance of baryons that we see? And how can we get that and ignore the whole other part of our universe that we think is actually just as important? And of course, then there's lots of different anomalies that have been measured, especially with neutrons recently. So this kind of points us to wanting to utilize experiment to understand the discrepancies here, but in new and exciting ways. And these are definitely possible at places like Oak Ridge National Laboratory and the European Spallation Source. So just quickly, the idea for the first kind of neutron oscillation experiment, primarily for neutron anti-neutron oscillation, was done back in France in the 1980s and early 90s at the Institut La Langevin in Grenoble, France. And they started with what they call the high flux reactor at ILL and produced neutrons, sent them downrange. They hit a reflector, and then they propagated roughly 76 meters and then hit a foil, and that foil was made of carbon. Now, if you know anything about cross sections, basically neutrons don't like carbon atoms very much, carbon nuclei very much. So neutrons themselves just fly through unencumbered through this foil. But if you happened to have a beyond standard model process happen where you would change spontaneously from a neutron into an antineutron, the annihilation cross-section of that antineutron is very large. And so it actually annihilates on this foil with almost 100% efficiency. And then there's just a beam dump down here where all the other neutrons go after they pass through unencumbered. And then all of the different particles that would emanate from that annihilation, blowing up that nucleus of carbon that it impacted on, can be collected by this detector. And back in the 1990s, they were able to come up with that this oscillation period was very long and very, very rare. So they created something that we call an ILL sensitivity unit. So we measure everything according to this experiment, how much better our future measurements could be. And just so people kind of get a little bit interesting here, they actually measured 0 signal and 0 background, which is a pretty incredible measurement with about 50% expected efficiency after 1 year of running. So what we plan to do is lengthen the time of this, lengthen the length of the flight path to allow for more observation time. If you remember that probability, it goes as t over tau squared. And so if you increase the flight time, you get great improvement in sensitivities. And this is possible at the European Spallation Source, but also Oak Ridge. And we can also better the carbon target design going forward. As far as the full experiment that we plan at ESS for this is just a brief schematic of this, where we would have a neutron source, a super mirror focusing reflector, surrounded by a magnetic shield that would, for neutron to antineutron transformation, allow for cancellation of that magnetic field from the environment, from the Earth, and then allow those states to come together theoretically. As they fly through vacuum for about 200 meters, they would impact on a similar detector of about 2 meters in diameter. And all of this is what we call NN bar, the all capitalized experiment. And basically, we think that this can improve the Institut La Langevin measurement by about a factor of 1,000 times in sensitivity with only 3 years of running, and other general improvements from the detector. And the great thing is that we think that we will have similarly low backgrounds, primarily because we have a different kind of neutron source. We have a spallation source, which actually has beam pulses that will allow for timing studies. The same kind of idea can be done for this neutron disappearance, this neutron oscillating into a dark sector idea. So the principal idea, of course, is that you, again, have some kind of a neutron source. You have your neutron here. You can count how many neutrons are passing through with monitors. And then you can have another monitor and a beam stop here. So you know how many neutrons came in, and then all of the normal neutrons would be stopped by absorbing material, basically. And if you had a magnetically shielded and then controlled region of disappearance space, what would happen is that all the normal neutrons would be absorbed. But if there was any kind of transformation that went into a dark sector, it disappeared, they would just fly right through. So you would have neutrons that would be absorbed, basically, but then some of them would have converted into this new species of dark matter. And then they wouldn't be absorbed, they could fly through to the next, what we call regeneration region. If we have similar amounts of magnetic field control, where again, we're basically varying that beta and we're varying the magnetic field strength, we would allow for potential regeneration where you can have a backwards second order oscillation, or sorry, second order process, and then be captured in the detector. And so this process, as I basically said, is fourth order in time, but second order process. And then in different places, if we were to do detectors in different places, we could measure different kinds of coherent signals. So we would be able to, for instance, look at the disappearance of neutrons at particular magnetic field values and directions. So the way that the signal would be basically found out is that you would look at the depth and the width of these particular dips if they happened at all. And if we had exquisite magnetic field uniformity, then these could be very, very narrow and be able to be observed definitively above background levels, which here are modeled in a Poissonian way, in a Gaussian way, sorry. And then as far as the height or the depth of these, if we have precise monitoring to the transmission of these neutrons, it allows us to basically count very quickly and very precisely. And in regeneration mode, basically we need large area, large background, or sorry, low background detectors in order to do this. And the nice thing is that unlike the N-bar experiment where we're trying to turn off all the magnetic fields through shielding, if we do this through magnetic field control, then all we have to do to make sure that the signal is real is we let the magnetic field come back in. We turn off the magnetic field control, and then the process should be able to stop. So this is just a first kind of shot of what we measured at the SNS back in 2019. This is a very, very high background detector, which we actually recently improved, but I won't show that. But where we're going next to the high flux isotope reactor is very, very low background. And this is the shot of the detector here after about an hour of running with no beam. And the environmental background rate here is about 0.3 counts per second, which is for our purposes great. Not the lowest background detector in the world, of course, but pretty dang good for a neutron detector. And all of this takes place right now, at least, at Oak Ridge National Lab, which is fully fitted with the high flux isotope reactor here and the spallation neutron source here. So the two differences between these is that one of these is produced in a nuclear reactor, and then one is produced, neutrons are produced via spallation, where you actually impact a proton target on, a proton beam on a mercury target, and then you can create about 30 neutrons per second that you have to control and put into beams. And the nice thing about the HIFER, high flux isotope reactor, is that there's a new upgrade coming. It's currently operating at 85 megawatts, and it's going to be upgraded to about 100 megawatts. And there's going to be new, what we call moderators, which will give us even slower neutrons, again, increasing that observation time for us. And the nice thing about this is that the Basic Energy Science Committee has recently come out with a statement that basically prioritizes this kind of facility for fundamental physics research, which to us is greatly, greatly encouraging, and we're trying to get in on the ground floor with this. And so this is the HIFER beam hall There are two beam lines here, CG1 and CG2. This is ours here, and we're currently going to be running in about February with this. And we can get about 10 to the 10 neutrons down beam here, which is awesome. And there's more to come with the upgrade here to 100 megawatts. And HIFER has been operating for 50 years nearly right now, but it will, it's actually almost 70 years, I think. And it will be operating for another 50 years thereafter, which is great for our fundamental physics. And there's also a new beryllium change-out happening here in this diagram that also will give us better neutrons that go higher than just the linear increase you would expect from reactor power. And again, our nice low background detector. ESS, of course, is another option here. And the European Spallation Source in Lund, Sweden has many different beamlines that are currently under construction. And we have access to two of them, wonderfully. One is what we call the ANI or high beam beamline here. And then the other is the full in-bar beamline. So we are currently in on the ground floor with both of these and are going to be submitting proposals for these very soon and have been in very good contact with a lot of the ESS folks. So this is just a closer look at the ANI high beam beamline. And basically there's plenty of space here. We prioritize this particular experimental setup, and actually our colleagues did as well, for fundamental searches because we had access to that corner, gave us longer observation times. And so the nice thing about this is that we can run these kinds of experiments at ANI high beam without the full operation of the expected beam intensity of roughly 2 to 5 megawatts of power. That will be ramped up slowly starting in about 2025, 2027, something like this. But we can actually start using neutrons even as early as 2023 with a lot of this. And that allows us to get really good science out early for fundamental physics at this new facility. This is just a brief overview of what that looks like. We have our moderator. We have different areas for experimentation, and then we have a potential upgrade area. But basically, all in all, we have about 54 meters of space here for our experiment. So this is getting toward the kind of space that the ILL previously had. But there's only about 5 meters of envelope space here, which makes, unlike their experiment at ILL, using a neutron reflector to reflect the neutrons downrange and preserve their coherence at the detector, a little bit harder. This is, again, just kind of an overlay here. If we consider just 1 megawatt of operation, which is enough for us, but not for other people, so we would be prioritized, then we can get about 10 to the 11 neutrons at the start here at our source. And this, after divergence, as the beam moves down the beamline for 50 meters, would give us access to about 10 to the 10 neutrons here. So we could have a region for disappearance for N to N prime, as well as regeneration for N prime to N. And then we'd have our detector after a few beam stops, etc. This is just what the beamline looks like. This is the recent simulation that we've done of the beamline with all of its optimizations. It's gigantic as far as the beam spot is concerned. It's over 8 meters by 3 meters. But in our detector, we have very, very high uniformity with a 1 meter diameter detector. And that gives us great capability to reduce, to basically have good background rejection. And it's also a very cold beam. It only has about 1,100 meters per second of average velocity. And that allows, again, our sensitivity to these processes to be quite compelling. And of course, we can then use all of these beams to explore all of these different oscillation processes. At ANI, for instance, we can get to, again, assuming about 1 megawatt of operating power, we can get about 1.25 ILL per year with just a 1 meter diameter detector. And that would be for N and bar, of course, but the nice thing about this beamline is that it allows us to do the research and design that we need for future measurements at the full NN-bar 200-meter long beamline. There's also many other different kinds of measurements that we can do using, again, R&D opportunities at both Oak Ridge National Lab and at ESS. And basically, given enough effort, we can complete many of these in the next 3 to 5 years across these. And I won't go through any of these really, but I did link papers. And if you are interested in the slides, there's backups that cover all of these. The one I will cover basically, or the two I will cover, is basically a regeneration here, where we would have, assuming about 50 meters of flight time at the high beam beamline at Oak Ridge and 1 megawatt of power, we could, with about a half meter detector radius, we could get to about 75 seconds of oscillation time, which would be about a factor of 5 better than the current limit. And that'd be with no reflectors used and with a very small number of measurements looking for these kinds of regeneration bumps here. And again, with the same kind of magnetic shielding and control regions that we would expect. If we instead look at disappearance, so just the first order process, then we would have, again, magnetic field control, but instead of a beam stop, we'd have a beam window. And we would be very, very carefully monitoring all of the neutron fluxes here at the beginning and at the end. And anything that has disappeared through these magnetic field control regions and through this window could be interpreted as a potential signal. And the wonderful thing about this is that you can actually, with a relatively small detector, you can come up with about a limit of about 340 seconds, which is a higher limit, of course, than when we had that second order process, and allows us to actually get into the same order of magnitude as the neutron lifetime itself, which is about 880 seconds. And effectively, if we were to do this measurement, even with just a year of running, this would almost eliminate the theory entirely, because the second that you have any of these processes like this that have a similar order to the neutron lifetime, you actually can spoil things like Big Bang nucleosynthesis. You don't get the right admixture of hydrogen, helium, and lithium that we observe today. There is one more interesting thing, and then I think I'm going to end for the day, where we can actually look for this larger four-part system, four-state system, I should say, where again, through the same kinds of magnetic field control, but with slightly different magnetic field configurations, we can come up with a similar kind of regeneration mechanism, which could induce this second order process, but allow for a production of antimatter actually. And again, with the magnetic field control and then an annihilation detector, similar to the one that we would expect to use at the full NN-bar beamline eventually after 2030, again, great R&D opportunity here. We could be able to observe these kinds of processes. There's other ideas of how you could potentially change the Fermi potential here, which would add a different field effectively. And then you could also check for different consistency measurements here, which effectively would put limits on the masses of many of these beyond standard model scalars, where you could relate different limits from different experiments together in this way. And that'd be highly useful for our ESS NN-bar experiment eventually, especially for things like detector design, but also background measurements in situ there at the facility. Okay, so I think I'm on time, but thank you all for your attention. Basically, I just wanted to summarize quickly that neutron transformation physics it's a really compelling kind of avenue within beyond standard model physics right now, especially with baryogenesis and dark matter in mind. And we can consider this kind of physics primarily in free neutron systems, like in beams or in bottles. The bottles I didn't really cover today, but you can also think of them happening, especially for NN-bar, in bound systems for neutron anti-neutron transformation. And that means that you can have complementary limits that happen across many different experiments, both with beams and inside of nuclei, like at Dune, for instance. And the great thing right now is that we're developing an international collaboration, and our kind of big publication that we are just now finishing has been accepted to European Journal Physics Journal G, sorry, and it's kind of our pre-conceptual design report, which we actually have due in 3 years. The conceptual design report is due in 2.5 years, actually. So the European funding agencies are very much behind us at the moment, and we're hoping to get DOE on board as well to create kind of a new fundamental physics opportunity for the whole world here, but based in Sweden. And we're very excited. So with that, I'll just leave you with a quick picture of our kind of pre-CDR here, which you can find on the archive. Again, it will soon be published, and this is just a few of our collaborators here at the European Spallation Source. This is the proton beam here that would be going toward the tungsten spallation target. And this is just a small kind of smattering of us. And then this is the chief ESS operator, beamline designer, I should say. And then this is ESS's head for fundamental physics. So there's a lot on the horizon, and hopefully some of you may kind of get interested in this. So yeah, thank you for your attention.